In this screencast, I'd like to discuss adjusted R-square. Most research articles that you read report a conservative version of R-square, adjusted R-square, which is often close to regular R-square, but it's always less than regular R-square. Why do we need to adjust R-square? R-square tends to overestimate the true value of R-square in the population. R-square is a sample statistic, and we're trying to estimate a population parameter, and it tends to overestimate that parameter. Like any sample statistic, population R-square is going to be equal to sample R-square plus or minus random sampling error. The special problem with R-square is that the sampling errors can only be positive, because even when you square a negative number, you get a positive value. This exerts an upward bias on R-square, so we need to adjust it downward. Here's the formula, and the key here is inside the big brackets. This is the adjustment factor. Notice a couple of things. First, let me explain some of the terminology. N, of course, stands for sample size. K is the number of independent variables in the model. So if you look at this, the adjustment factor will always be greater than 1. In fact, the smaller the sample size and the more the number of independent variables in the model, the larger the adjustment factor is. And see that, so if you're dealing with large samples, the adjusted R-square is very close to regular R-square. But with smaller samples, like the state sample, the two numbers are going to be more noticeably different. Just to review those points, the adjustment factor will always be greater than 1. All models have at least one independent variable, so the adjustment factor can never be smaller than n minus 1 divided by n minus 2. As sample size goes down, and I should add as the number of independent variables goes up, the adjustment factor also goes up. So if you have a sample of 500, 500 minus 1 divided by 500 minus 2, the adjustment factor is 1.002, very weak adjustment on R-square. But for sample sizes that are smaller, like say n equal 50, 50 minus 1 divided by 50 minus 2, the adjustment factor now is up to 1.021. To return to our example in the text, we calculated R-square at 0.19. Here are the elements here. The size of the sample is 50 because we have 50 states. We were using one independent variable, so k equals 1. So adjusted R-square is going to be equal to 1 minus 0.19 times 1.021, which is the adjustment factor for our particular example. And that works out, if you do the math here, to an adjusted R-square of 0.17. So we started with 0.19. We had to adjust it downward to come in with a more conservative estimate of R-square, and that adjustment gives us an R-square, adjusted R-square of 0.17. So, after adjustment, we conclude that education explains 17% of the variation in turnout across states.